Hello, this is Mr. McCullum, and this is your lesson for January 20th, 2011. So, the other day, we had started off by talking about gravity. That is, the vertical drop, air resistance, the things that cause other things to fall. But let's change the tone a little bit and talk a little bit about projectile motion. Now, when you think of projectile motion, what comes to mind? How about this? If you were thinking of a projectile in general, we normally think of a projectile that is launched straight forward and has a certain path, a certain speed, a certain direction ultimately, right? Well, projectile motion, we're interested in the curved path that it follows, right? So, let's think of this for a minute. Here I have in my hand a rubber band ball from Office Max. If I were to take this rubber band ball and throw it straight ahead, what happens? Let's try it. And it goes every which way, right? But what do you notice? What do you notice when I throw it at the wall?
Well, to better answer this question, it's probably best to look at the diagram on page 41 at the bottom. Here we have a picture of a baseball pitcher that's throwing a baseball in a horizontal direction, right? The book says after the ball leaves the pitcher's hand, the ball's horizontal velocity is constant. Think about what that means. Well, throwing it in the direction that she's throwing it, it means that once it leaves her hand, the actual velocity that it's traveling at stays consistent, or doesn't change. It doesn't speed up or slow down and speed up or slow down. It stays constant. Which leads to the point B. It says the ball's vertical velocity increases because gravity causes it to accelerate downward. So that means you have a combination of two forces, right? It's also it's traveling in the right direction because of the pitcher's hand. She's accelerating it to the right, but gravity takes a hold and pulls it downward. So it's now following a combination of two forces, a curved path. So, which brings us to point C. The two motions combine to form a curved path. So this little dotted line that you see is a combination of the pitcher's hand throwing it to the right and gravity pulling downward on it. So this makes a curved path.
Okay, now let's move on to the lab part of this class period, okay? We're going to be doing something called the Marshmallow catapult. Now, can anybody tell me what a catapult is? Well, a catapult is something that uses projectile motion to launch objects. So, before you saw me throwing the rubber band ball against the wall, I was launching the rubber band ball, that is the projectile, at the wall, where it subsequently bounced off and came back to me. Okay? It had a certain speed, it had a certain direction, but most importantly, it had an angle. Alright? So it says, in this lab you will build a simple catapult and determine the angle at which the catapult will launch an object the farthest. Yay! So, we have some materials we're going to be using. You're going to need some miniature marshmallows. Now, if you don't have any miniature marshmallows, you may use a standard cotton ball. The application is the same. So, for the purposes of this, I'll use cotton balls since I don't have any marshmallows myself, but I will the day of the actual lab when I do it. You'll need a meter stick, a protractor, a plastic spoon, some duct tape, and a wooden block that's measured 3.5 centimeters by 3.5 centimeters by 1 centimeter. Alright, now before we actually tell you what to do with the lab, we want to ask a couple of questions, but one is most important, okay? Number one, it asks, at what angle, from 10 degrees to 9 degrees, will a catapult launch a marshmallow the farthest? That's the problem we're trying to solve for this lab, okay? So, under number 2 on your worksheet, you're going to fill in the part where it says, write a hypothesis that is possible to answer your question. So again, what angle from 10 degrees to 90 degrees will a catapult launch a marshmallow the farthest? Now, let me go into a short explanation about what angles are, in case you aren't familiar with them.
Okay, so what are angles? Well, if you remember back to the pre-geometry part of your math classes, you might have seen a graph that looks something like this, and something called the unit circle. The unit circle represents a series of measurements that give us an actual circular rotation around the graph, which gives us an angle of measurements. We have a straight line going in the x direction and a straight line going in the y direction, the coordinate system most of you are familiar with. And if you draw a circle around this intersecting line, you can draw other lines that intersect the origin point of the graph, which gives you a certain angle. But more simply, we'll use something known as a protractor. A protractor gives you the ability to measure these lines either on a piece of paper or by finding a point flat at the bottom of the protractor and rotating your object from the origin, or the bottom flat surface if you will, and going up to any certain number of degrees, and you can draw a line to that actual point that you're rotating the object from to come to an actual angle. So for the purposes of this lab, we will be using a protractor to measure the actual angle in degrees using this protractor method as I...
Okay, so here's our setup. We have our plastic spoon catapult taped to our little wooden block. Here we have our protractor, and here's our measuring stick. Okay? Now I'm going to put the camera down. Hopefully this works the way I want it to. But I only have two hands. So, so by default our protractor will be at 10 degrees, right? Now the instruction sheet says to start with your wooden block at a corner of your protractor, right? So hold your catapult with your fingers, so that way I know what's happening with me is it's going like that. It's falling over. So hold it with your fingers, and you see here at the bottom how it's flat, and then you find 10 degrees on the protractor. What's going to happen is you're going to rotate this around to 20, to 30, to 40, to 50, etc. until you get all the way up to 90, which should be like that. Alright, now for some people it might be more beneficial to actually take and draw the lines on your paper and just continue to rotate on each one of those lines, and I'll post a photo about that in a second if I remember to. But anyway, we're going to take our marshmallow or cotton ball and place it in the spoon, and we're going to flick our spoon up, and we're going to record the distance that it went. So for this particular demonstration, we went exactly 27 centimeters for 10 degrees. Now let's rotate it to 20 and do the same thing. Well, that wasn't a very good flick. Let me try again. Okay. We got 20 this time. Let's rotate to 30. 16. Let's rotate finally to 40. One more time. Looks to be about 8. Okay, so I think we can see the pattern that's happening here. For the angle that we increase our flicking, we get less distance covered, right? So what would be your hypothesis if we were to go completely to 90 degrees? Alright, so repeat that and record on your data sheet down here at the bottom in the boxes. Alright. You're going to be doing this 2 times, okay? Your first distance you're going to record in distance 1, recorded in centimeters, and then distance 2 in centimeters. And then you're going to get an average distance. You're going to divide, you're going to add up distance 1 and distance 2, in this case for 10 degrees. Then you're going to divide it by 2 to get an average distance. You're going to do the same thing for 20 degrees, add up distance 1, add up distance 2, then divide by 2 to get an average distance. Do the same thing for 30 through 90. Alright? Under Analyze the Results, you have 2 questions. It says, at what angle did the catapult launch the marshmallow the farthest? Explain any differences from your hypothesis. So that pretty much is self-explanatory. What angle did you use that it launched the farthest? And in fact, I demonstrated that myself. Explain the differences from your hypothesis. That is what you thought at the beginning. Alright, so here's a draw conclusion question for number 2. At what angle should you throw a ball or shoot an arrow so that it will fly the farthest? Why? Support your answer with your data. Well, so for homework, a good thing might be to do, if you want to, is to find a ball. I don't want you shooting any arrows, obviously, because that's dangerous unless you have unless you're skilled in archery, and you definitely need your parents' permission to do that. But find a ball and see how far it goes when you throw it. Try the different angles.